And at the end of the last lecture, we were talking about clusters of stars and how we can plot all of the stars on an HR diagram in a cluster. And the unique thing about a star cluster, like you see here, is that all the stars were formed around the same time. Okay, and so recall on an HR diagram, if the stars are in the main sequence, burning hydrogen to helium, in a cluster, stars will form in all different sizes. The lower mass stars will be redder and live longer. The higher mass stars will be bluer and live very short lives, as short as a few million years, most massive cases. Our own sun is kind of in the middle, will live about 10 billion years. And so what we're seeing is that if you plot different star clusters, so here we have 4 different star clusters plotted. What's interesting is you can actually see the age of the cluster, because the stars that were high mass and so don't live very long have all died off. And for older and older clusters, more and more types of stars have died off. So, for example, this cluster, H and Chi Persei clusters, are very young, because you're seeing stars begin to die that are only a few million years old. And you don't see many stars younger than that. The Pleiades, about 100 million years old. Stars of O and B types are mostly dead. Hyades, about 650 million years old. Stars of O and B and beginning into A types are beginning to die off. So you see that the really hotter stars, in other words, the ones that started off with younger masses, with higher masses, and so can't live as long, have died off. And you actually see what's called the turn-off point, where these stars are beginning to now become giants. And that's actually what we're going to talk about in the next lecture today, is what happens. Well, we'll start going into the details about how stars live and die. Okay, specifically, we'll begin to talk about how stars run out of fuel. So we see things like this. So this is kind of shows a turnoff point around the age of our sun, for example, where you have stars about 10 billion years old beginning to die off, entering the phase where they're no longer fusing hydrogen to helium, become these giants, and then they die and become white dwarfs. And to kind of emphasize the sort of understanding I expect from you when it comes to HR diagrams, there's a couple of questions that we'll just do together. So like, for example, what do we mean by the main sequence turnoff point? What does that mean? Well, it's the spectral type, so the color of the hottest main sequence star in a star cluster that tells us the cluster's age, because any stars, right, if that's the hottest star that you see, you don't see anything hotter, which means that anything hotter has burned out already. So it kind of tells you the age of the star cluster. And as an example, like suppose we have these 3 possibilities. Which example has the youngest star cluster? So we have a diagram that shows main sequence stars of every spectral type except O, for example. That's answer A. What answer B is, it shows main sequence stars of all spectral types that shows main sequence stars of only spectral types G, K, and M. Okay. Or we have one that shows main sequence stars of all spectral types except O and B. So remember, O, B, A, F, G, K, M. O is the hottest. So if we have a diagram that shows main sequence stars of every spectral type except just O, that's going to be a very, very young star cluster. It's only the stars that are a couple million years old that have died off. Whereas C would be next oldest, all spectral types except O and B, and then B would be the oldest. Okay? So the youngest in this case would be, it would look like, well, it'd be similar to this diagram, except it would, well, yeah, very close to this diagram. This shows every spectral type except O. Okay, so the youngest of those options. And so that's what I wanted to cover about kind of rounding off our understanding of the lives of stars on the main sequence with these HR diagrams. So these HR diagrams are going to be pretty important. So make sure you ask any questions now. If you have any questions at all about stars, about HR diagrams, like seen here. Okay, if not, then we'll move on to the next lecture. Which is
what?
Not
here?
So we talked about how in the last lecture, two lectures actually, covering all about kind of how you catalog stars. We look up in the night sky, we catalog them, and we measure their luminosity, their distance. Well, we measure their apparent brightness and a distance, which gives us their luminosity. We measure their spectral type of color, and then we can plot them on HR diagrams, right? And so today we're going to go into some more detail of the theory of the how stars actually live their lives, and then we'll talk about how they die. And so these, just by the way, when I show you photos, these you'll see some nomenclature describing, what we're looking at. And these, there's a number of different star catalogs that are very famous that you should just know to recognize the reference. So, for example, if you see M in front of a number, that's Charles Messier's catalog from the 18th century. This was the first kind of catalog of just various objects that is still used today. So there's only 110 objects. So this is the 18th century, before really good telescopes could observe a whole lot. So things like the Andromeda galaxy, okay, have names Messier catalog number objects up to 110. Later in the 19th century, the NGC, or New General Catalog, has about 8,000 galaxies, nebulae, star clusters. This covers pretty much everything you're ever going to see with your own eyes in the night sky. You only begin to need anything more like this index catalog that's a supplement when we start talking about the Hubble, the telescopes being able to see really small things that normally you're not going to ever see. But just for example, the Andromeda galaxy is M31, so the 31st Messier catalog object. It's something that's really big, and so even in the 18th century, it had been cataloged. But alternatively, NGC has it as number 224. So these are the sort of things you'll see when we show pictures of various objects. All right. So what I want to do today is start off talking about, this is going to be another two-part lecture. I'm going to start off talking about how stars form in the first place. What we see are regions that have a lot of gas and dust. That would be star-forming regions. Stars are mostly hydrogen, okay? Just like our own sun, just like our own solar system is mostly hydrogen. It's the simplest element. It was formed during the Big Bang. In outer space, there's just various regions with more hydrogen than other regions. And they tend to also have little bits of other stuff, little dust. Dust obscures light. So you see things like this. These are called nebulae. So this is one example, one of many examples I'll show you. It's called the Dark Tower in Scorpius. And what you're seeing is kind of a slightly darkish region here, where there's a lot of dust accumulated, signaling that there's also a lot of gas in there. Gas and dust tend to live together. And those are regions where stars are going to form. Right? Gravity is going to slowly compress that over time to the stars. This region might form hundreds of stars. And we'll also talk about how, what gives off this color around the edge. It turns out it's being warmed along the edges of this cloud of gas and dust by stars nearby, and so it's giving off this glow. There's another famous one, the Horsehead Nebula in Orion. If you look up at Orion's belt area with a telescope, take a long exposure photograph, you see these beautiful Orion Nebula with, for example, this horsehead looking feature. And it's a dark cloud of gas and dust, as you can see. This is where you're going to have lots of stars forming in the future. And ultimately, all of this is coming, or all of this is part of what we call the interstellar medium. Okay? ISM, interstellar medium. It's all just the gas and dust between stars in the galaxy. Okay? And it's about 99% gas, but 1% dust, just like our solar system. Remember, our solar system is mostly hydrogen and helium, and that little bit of other stuff is what form the planets, which still will just make a small fraction of the total mass of the solar system. And our solar system ultimately formed from this stuff. So the same way we're going to be talking about today. It's mostly hydrogen, helium, and then a little bit of dust. And when we talk about the interstellar medium, there's various places we can talk about the interstellar medium. We can talk about regions where there's not a nebula, not a nebula, or we can talk about really dense regions like nebulas where stars are going to form. And so the quote unquote vacuum of space is not a vacuum. It's an interstellar medium that's composed of and somewhere between like 1,000th to 1,000,000 or so molecules per cubic centimeter, depending on where you look. On average, it's about half a molecule per cubic centimeter. Little box. Like in normal air, by the way, like in this room, it's about 10 to the 20. So like a trillion billion molecules per cubic centimeter. In the space, on average, about half a molecule. And okay, you have this stuff out in the interstellar medium. Is it going to just all compress to form stars? Well, it depends. So what prevents things from getting compressed? Okay. Well, things are in what we call hydrostatic equilibrium. That is, yeah, gravitational attraction wants to pull things inward, but things also have a pressure that want to push outward. Okay. So typically things, that aren't compressing are in what we call equilibrium. The pressure outward is balanced against the gravitational pull inward. Think about the Earth. Okay, the Earth right now is not compressing. It's not pulling all in, right? It's in equilibrium. There's gravity pulling inward, and there's something pushing outward. Okay, we'll talk about that today. There's different types of pressure that can push outward. There's a gas, like in a one of these star-forming regions. In that case, the pressure depends on the density, the amount of stuff, and the temperature. The temperature raises, that pushes outward. Okay? We'll talk about some other examples today of things about pressures. Under what conditions can gravity overcome that pressure for a gas, like in a nebula? Well, it has to overcome the pressure due to that temperature rise. So remember, we talked about as stuff pulls in under gravity, like when our own solar system formed, it heats up, right? And that's because gravitational potential energy is converted into thermal energy. So the temperature goes up, and then it wants to push back outwards. It doesn't want to keep collapsing because it gets too hot. So there's a number we can put to like how massive something needs to be so that it could overcome that and keep pulling in. It's called John's mass. Okay, and basically it's about the main thing to understand is it depends on the temperature of the gas, and it depends on the mass. The mass that's needed depends on the temperature of the gas. Okay, and the density of stuff in the interstellar medium. So overall, higher density stuff at low temperatures require less mass in order to form a star. Okay. Here's a simulation of what you might, what a computer says should happen if you just take a giant sphere of gas and just let it try to collapse under gravity. Okay. Because this is what we think happens in the interstellar medium. You have some regions with more gas, some regions with a little less, the regions with a little more gas and dust try to collapse under gravity, but it's complicated because things get warmer, the warm regions want to push back, and you need a simulation to see exactly what's going to happen. And what happens, it kind of forms this spider web-like filaments of regions that are hotter, that's why they're showing up yellower, where there's lots of contraction happening, so it's heating up, and where we call these filaments, where you have really dense star-forming regions. It will turn into the parts of nebulae that show up as having those darker regions of gas and dust. And indeed, what we see is something very similar to what you see from these simulations. There's a simulation, and we see stuff like that. Okay, we see regions that have a little bit more gas and dust than the rest of the interstellar medium, and they form these like structures, these kind of filamentary structures where stuff under gravity is compressing. And this is called the elephant's trunk nebula in Sepia. So this whole region has more density than the average interstellar medium, but these particular areas, like this elephant's trunk here, has an extra lot of gas and dust. That's really where you're first going to be forming stars. Here, if we so here is this elephant's trunk. Here's elephant's trunk, kind of zoomed in a little bit in the visible part of the spectrum. And the thing you notice about the visible part of the spectrum is that there's this dark region that has a lot of gas and dust where you can't see through it. So it's a really good indicator that this is where there's lots of stuff that's going to be able to form stars. But it's contracting, and so it's going to warm up. So if we switch, instead of from visible light, we switch to infrared light, you see like this. So this is heating up both because it's collapsing under gravity, but also it absorbs energy from stars, nearby, because it's a star forming region. And in both cases, what it does is it glows in the infrared. So we can exploit the fact that things kind of near room temperature emit lots of infrared light. And so we can see all this gas and dust glow. Here's a comparison. So both photos in one. So here's the visible part where you see all the gas and dust, and then you see that it's warming up when we see it glow in the infrared. Now, what I want you to understand is the only reason you can have a star form is because the energy that, so when these clouds of gas and dust heat up as they're contracting, it has to be able to radiate that heat back out. That's the only way it can continue to eventually collapse. So the process I want you to imagine is this gas and dust starts collapsing, but it heats up. So it slows down and it stops collapsing. But so it's warmer, but luckily it's emitting all that infrared radiation, so it can cool down and then slowly continue collapsing. So there's this kind of dance going on in outer space where things are trying to collapse, but they heat up as they collapse, so then they want to push back out. And so it's kind of a slower process. It's not just gravity happening to form stars. There's also this pushback. So if there wasn't a way for things to release energy, nothing would ever collapse to form stars. Okay? It's only because they radiate energy that they can form stars. Now remember, this is there's a story we talked about in our own solar system, which is what we're talking about here now, but just for other stars. Of what happens when you have this cloud of gas and dust collapsing in a given region. Right, it starts out kind of like that simulation I showed you, like this giant sphere, but it slowly starts to collapse. Gravitational potential turns into thermal energy, into the heat. So it gets hot, starts to flatten, and it starts to spin faster and faster. Remember, that's due to conservation of angular momentum. Right? And this is what we tend to see when you look at other star systems. Each one heats up, flattens, so forms kind of a disk, and you see spinning around some axis. And remember that you tend to form more circular orbits, like our own solar system, because if things don't have circular orbits, they bump into each other. Right? They knock each other out of non-circular orbits until they're kind of in their own lanes. Right? And we also mentioned before this kind of fun fact, which is that, remember, the sun contains 99.8% of the mass of the solar system. But in physics, we like to talk about angular momentum, right? This is what's at work when we talk about, the process by which when a skater pulls in his or her arms, spin faster, and what causes the solar system as a whole to be rotating right about some axis. The sun only accounts for 5% of the solar system's angular momentum. In other words, 20 times the angular momentum of the solar system is carried by things like Jupiter, Saturn. So in order to create a solar system with that much angular momentum around the star, somehow material in the early solar system must lose angular momentum. That is, the star, right? So in other words, the solar system has a lot of angular momentum. How does all that mass then get to the center where the sun is? Right? Think of how hard it is if you have angular momentum, like a ice skater skating. How hard it is to pull in your arms, right? Because you spin faster and faster. You know, at a certain point, the sun would be spinning so faster it would rip itself apart. So there has to be some way of solar systems getting rid of some of their angular momentum as stuff falls to the center to form a star. And so I just wanted to, this is kind of one of these neat things we see when we look out at newly formed solar systems, is we see these jets often pointing in two directions where there's swirling matter where it's able to release some of its angular momentum so that that material can fall to the center and form a star. Okay. The reason why these jets exist is because, similar to why a planet or the sun that's spinning around its axis has a magnetic field, and magnetic fields corral charged particles along magnetic field lines. So essentially, these early solar systems have a north and a south pole. They're spinning, and so charged particles get pushed along these field lines, twirling around to help lose angular momentum, and we see this. So here's some cool pictures showing newly formed solar systems. Here's like a nice side-on view, for example, where you see these jets, we call them, along the axes. Here's one here emitting to the left, to the right. Here's one emitting to the right, to the left. And as you see at the end, just like if you have a jet of water, you know, it hits the interstellar medium. It kind of starts to stop eventually because it gets slowed down, like here and here. So these jets, it's like if you emit a jet of like colored water in an aquarium, at first it comes out, but then it kind of blooms out and slows down, and that's what you're seeing. Here's a really nice one. So here's the newly formed solar system, and you see this really cool jet coming out this way. There's also one that you can't see as much because it's obscured by dust pointing this way, and then you see it, the shock front as it hits the interstellar medium at the bottom and top. We see this a lot in newly formed solar systems. The way they're losing angular momentum so that matter can get to the very center to form the star. What you realize is if a solar system formed without any rotation, so imagine just taking all of this mass without anything rotating throughout anything else, just releasing it, it would all just fall to the center. And so you could never have any planets. The only reason we have planets in our solar system is because we have rotation, right? And indeed, the planets have most of the angular momentum in our solar system. That's what prevents them from falling down to the center, right? Because angular momentum is conserved. They can't just lose angular momentum. Except in the early solar system, little charged particles can be emitted out jets along the north and south poles of protostar. Now, let's think about what happens before a star is formed, or as it's forming. So you have gravity causing a cloud of gas and dust to shrink. This, what we call a protostar, is heating. It gets hotter and hotter as it's shrinking down. At a certain point, it gets so hot that you can have hydrogen fusion. Now, we talked about hydrogen fusion. We'll have a little review today, but we talked about hydrogen fusion when we talked about the sun. Right? It takes a few million degrees, right, at the center of the sun in order to sustain protons and protons colliding to form helium. That's what powers the sun. And so this cloud of gas dust that had been contracting eventually heats up to the point that you have fusion that adds back more energy and pushes creates an internal pressure that pushes outward so that the star no longer contracts, and it reaches what we call hydrostatic equilibrium. That is, it's no longer expanding or shrinking. Gravity is pulling in. The internal pressure from fusion is pushing out. It has a pretty stable size and surface temperature. It typically takes about 30 million years for a star like our own sun to go through this process of shrinking down until it's warm enough to ignite fusion. Much more massive stars, it goes much more quickly. Everything goes more quickly for more massive stars. Now, we call a star a main sequence star. Not only has it ignited fusion, but it's entered the phase of life. This one, billions of years. Okay, it's entered the phase where it's stable, it's in equilibrium, and it's just burning that hydrogen to the source. Okay? So there's a period before the main sequence where it's still kind of shrinking, and it hasn't yet, or it has just ignited hydrogen fusion, and maybe it's ballooning out just a little bit more, and it hasn't quite reached equilibrium. That takes about 30 million years again for a star like our sun. But once it's reached a stable size, stable temperature, using hydrogen and helium, and everything we talked about in the last lecture about HR diagrams plots, right? We look at its luminosity and its, you can understand its size, you can understand its stage in life, its mass, and so on. Any questions so far? All right, so we've touched on the masses of stars, right? The range, upper limit is called the Eddington limit. You never see a star form. Well, you can see it form starting more than 150 solar masses, but you're never going to form a star that's more than 150 solar masses, because that's the point where it would be so luminous that it's going to blow itself apart. We saw an example of that in Eta Carinae before. And then the lower mass limit is about 8% of the sun's mass. Below that, we call it a brown dwarf. It just never can heat up enough as it's contracting. There's not enough energy there to be turned into thermal energy or to cause ongoing hydrogen to helium fusion. Those are called brown dwarfs. And yeah, this is a reminder, right? We've gone over this a number of times, but it's a good example of something that hopefully you all remember. So let's ask this question about the upper limit. That is, why don't we expect stars above 150 times the mass of the sun, right?
No stars are expected with
Just leave it like this.
mass greater than 1.
All right, so this is on the more massive end of the spectrum. Why is there a point at which stars can't be any more massive than 150 times the mass of the sun? Give me 10 more seconds. Yeah, so most people got the right answer, right? So
Sometimes.
it's not at all, it's not E, it's not that they would be too massive for hydrogen fusion, it's quite the opposite. In fact, as stars get more massive, they are fusing at a more and more rapid rate. They're burning through their fuel faster and faster. They're much, much more luminous. Above 150 solar masses, they would literally blow themselves apart.
So it's really my first choice.
Now, here's these HR diagrams. We spent so much time familiarizing ourselves the last lecture. Remember, we talked about the main sequence. This is where stars are fusing hydrogen to helium. They're along this line that moves from the upper left to the lower right. And there's a lot of cool information here. We see that there's stars that are not on the main sequence, stars that are running out of hydrogen fuel, become red giants. We'll talk all about that end of life stage of stars. And then the dead stellar relics called white dwarfs are down here. And these are smaller. So these are larger and redder, these are smaller and bluer. And on the main sequence, we see a variety of stars ranging from the redder, less luminous down here, to the bluer, more luminous up here. These up here are more massive, these down here are less massive. These up here, the bluer ones, the shorter lives, the ones down here, the longer lives. And remember, if you look at the top here on this diagram, you have our spectral type, O, B, A, F, G, K, N. So this is a good reminder here. You should certainly by now be able to answer a question like this. Which type of star spends the shortest time as a main sequence star? This is what we're going to be understanding in the next couple lectures, is what's going on as a star dies. But by now, we've definitely learned how long stars of different spectral class live.
Is not O. M. Is it M? I think it might be
10 more seconds. Okay. And again, good job. Most people got O. So just remember, O, B, A, F, G, K, M. O is the bluest, hottest of the spectral type of stars. It lives the shortest life. It's the most luminous. It burns through its fuel the fastest. Okay. They typically live just a few million years. Very, very, very short. Whereas a G-type star, like our own sun, lasts about 10 billion years. We're about halfway through that life now. That's before it exits the main sequence, where it rapidly burns through the rest of its fuel and it dies. Now, let's think for a second about this concept of hydrostatic equilibrium again, and what prevents a star, say when it dies, from just, let's think of either possibility. When a star dies, when it runs out of fuel, so there's nothing anymore preventing it from collapsing, versus when a star never even enters the main sequence. Maybe it's not massive enough. It's like a big Jupiter. What prevents that thing? You know, gravity is still pulling inward. What prevents it from contracting all the way down to a point? So let's remember a couple of things. One thing, if you have a gas, you have the ideal gas law. Like if you put gas in a cylinder and you start trying to compress it, you're pushing on it, what happens? Well, as you exert more pressure on it, right? The temperature goes up, for example, or if you volume, the pressure goes up and the temperature goes up. This is all these kind of relationships are expressed by this ideal gas law, PV equals NKT, right? If, for example, if you hold the temperature constant, then if you try to compress your gas to a smaller volume, the pressure goes up, it pushes back, right? So this is relevant to a gas. So one thing to remember is like in a star, we talked about hydrostatic equilibrium. That is, you have this pressure in the inside of the star pushing out against gravity, right? If the star, so the star has this fuel that's adding heat energy to the inside of the star, exerting more pressure to counteract gravity, right? But what happens if the star runs out of fuel and there's nothing to push back? Well, remember, then we revert to what we talked about before the star was fusing hydrogen to helium. It was contracting, heating up. As it heats up, it pushes back outward, but it radiates that energy out into space so it can continue to collapse. Well, what happens? Does it just keep collapsing forever? Well, there's some things that can prevent it from collapsing forever. And one thing we want to consider relates to atomic theory. So as a reminder, here's a picture of an atom. Two main things to understand is that the atom's size is determined by the orbit of the electrons. So this is negatively charged electrons, about a tenth of a billionth of a meter is about the size of these orbits. So 10 to the minus 10 meters. And then they're orbiting a small positively charged, what we call a nucleus. It's about 100,000 times smaller than that. And so these are atoms, and they don't like to squish together. Incidentally, I have this next slide just showing the reality doesn't quite look like these classical orbits. It more looks like this. We call it this kind of like a cloud of probability. But the idea is that an atom does have a size. It's about a tenth of a billionth of a meter. And these atoms don't like to overlap. The reason why is because no two electrons can occupy the same state. So these electrons that characterize the edge of an atom prevent atoms from smushing together. And as you try to smush atoms together, instead of like a gas here where they just kind of exert more and more pressure, it's more like musical chairs. It's more like there's just some number of atoms that could be pressed together and then they just won't budge anymore. And they start exerting back out more and more what we call degeneracy pressure. Okay. Here's some facts about degeneracy pressure that I want you to understand, okay? The thing about degeneracy pressure is unlike the other kind of pressure we talked about, like in a star, you heat up the inside, it pushes more out, right? Degeneracy pressure doesn't care at all about temperature. Degeneracy pressure only cares about the fact that atoms can't squeeze together beyond a certain point. Now, what's true is that degeneracy pressure can halt the contraction of a star even when there's no fusion. So if a star runs out of fuel, eventually it reaches a density where all the atoms are just pressed together, and degeneracy, the core of that star collapses. But also the star never even enters the main sequence. So say it's less than 8% of the mass of the sun. So 0.08 solar masses, so like a really big Jupiter. Okay, it never becomes a true star. So what happens? Does it keep collapsing forever? Well, no. I mean, we know like the Earth doesn't keep collapsing. Both the Earth or Jupiter or any what we call brown dwarf, a star that never enters the main sequence, are prevented from collapsing by what's called degeneracy pressure. Okay, in the core of the Earth, the core of a brown dwarf, there's a lot of pressure inward, but it stops, it resists collapsing any further due to the fact that atoms don't want to occupy the same state. And even though this is a kind of an intro level course where we're not learning quantum mechanics, this is a case though where you get to learn something that is a consequence of quantum mechanics. When you hear about quantum mechanics, it actually is important for daily life. It's why tables are solid. It's why my hands don't go through each other right now. And it's why the Earth doesn't keep collapsing under gravity. It's due to this quantum mechanical effect called degeneracy pressure. And this is why stars, even in their core, even if their core is not supported by thermal pressure, not like a gas that's just hot and pushing outward, they can have a core that's just solid that won't collapse due to what we call degeneracy pressure. And this will be important later on in this lecture. Okay, so for example, a brown dwarf. These are star-like objects. We say they're star-like because we can look out at the sky and we can see some, only if they're close, because they're not very luminous. And they're kind of just red. They're glowing red, failed stars. They never were large enough to create enough heat in their cores to ignite hydrogen fusion. So this is something, anything less than about 80 Jupiter's worth of mass, or less than about 8% of the mass of the sun, just form, so they do get really hot. Like they can get tens of thousands of degrees and glow bright red hot, but they're never hot enough to form fusion. Okay, so from then on, they just cool off slowly over time. But they don't collapse to a black hole. They're supported, just like the Earth is, by electron degeneracy pressure. This is just an artist's conception of, an example of large Jupiter-like object. It's a brown dwarf. But we can see them in the infrared, especially because they emit lots of light in the infrared. They're not so bright that we can see them easily with visible light, even though they can glow red. Here's an infrared looking in the Orion Nebula, and there's some, close enough. We're looking in the infrared that we can see brown dwarfs. So a lot of these points of light in this image, again, this is an infrared light, are these kind of warm, glowing, big Jupiters that never formed stars. Okay, they never entered the main sequence, we would say, because they didn't. They're not burning the hydrogen fuel in their cores. Now, if we have a brown dwarf and it's not fusing anything, what's going to happen to it? Well, it's just going to remain a brown dwarf forever, cooling off till the end of time. Okay, it might start off 1,000 degrees, but it's just going to slowly cool off because there's no heat source. Any questions so far about, for example, brown dwarfs? Now, brown dwarfs are more common than most stars. In general, the lower the mass, the more common it is. Just like there's more grains of dust in the world than there are big boulders. But they're harder to see. They're harder to see because they don't glow very brightly. Okay, so we're going to talk about the life and death of kind of two major categories of star in this course. What we call quote unquote low mass stars, of which our sun is an example. And then we're going to talk about quote unquote high mass stars. Now, in reality, stars are all possible masses, but broadly speaking, there's kind of two different lives that we can talk about: sun-like stars, low mass stars, and high mass stars. So we're going to first talk about low mass stars, and we're not even going to get to high mass stars today. We'll do that next one. So here's a broad outline of, just for example, a sun-like star. So let's say, take a star that's about 1 solar mass, and we'll call this a low mass star. So its life, broadly, consists of first that 30 million years or so, really a blink of an eye in the life of a low mass star, but about 30 million years to start from a nebula and then collapse into a protostar. And then on point number 2 here, it enters the main sequence. So the majority of its life is on the main sequence. In this case, it's kind of a yellowish color, sun-like stars. It's like a yellow color, fusing hydrogen to helium through proton-proton fusion. About 10 billion years, most of its life on the main sequence. And then we'll talk in detail about what happens as it runs out of that hydrogen fuel. On the HR diagram, it moves to the upper right. It becomes redder and larger. We call it a red giant. And that's when its core has been mostly replaced by helium because it's fused hydrogen into helium. And so it's accumulated all of this helium, right? And so you have this inert, we say, just big ball of helium in the core, and you're still fusing some hydrogen, but it's in a thin shell around the core. And that's when you begin to become a red giant. And this phase lasts for about 1 billion years. So about 10% of the star's life. Next, everything else happens very, very rapidly. So next, eventually it gets hot enough that it starts fusing the helium, okay? And remember, I told you that all the elements that were made out of everything, including carbon, is made in the cores of, well, somehow through stellar processes, right? Either in the cores of stars or when they explode. And once helium starts fusing, it forms carbon, okay? So that's where carbon comes from. And this happens very, very rapidly now. So the star's life is rapidly coming to an end. It starts fusing carbon. It gets big again at another red giant stage called double shell fusion red giant, where you're both fusing hydrogen, the remaining hydrogen, and the remaining helium, as an inert core of carbon is building up in the center. And then finally, the star kind of violently explodes when it runs out of fuel, producing what's called a planetary nebula. Now, the planetary is just an archaic reason why it's called that. It doesn't have anything to do with planets, but it forms a nebula again. So it's kind of the life cycle of stars goes in a circle. The star kind of explodes, produces a nebula that can then form a new star in the future. And it leaves behind that core of carbon called the white dwarf. So that core that's left over at the very end of stuff that couldn't be fused is just a giant ball of carbon. And it's very small, it's very blue hot. It's not very luminous because it's so small, but it is very blue. It's called the white dwarf. And that can last forever, except it slowly cools off because this white dwarf doesn't have a fusion source. It doesn't have a source of energy. So it just cools off till the end of time. Okay, we'll talk about later, high mass stars have a different life, including they can become black holes or neutron stars at the end of their lives. But a low mass star will end its life, including our sun, will end its life as a white dwarf and a nebula. It'll create one of these beautiful nebulas that can then help form stars in the future. So this is the process that we're going to go into some detail discussing. Any questions about anything on this list? So one thing to note, right, just from this list, you see that a star spends about 90% of its life on the main sequence. 10 billion years. That's what we say when we say like the life of our sun is about 10 billion years. 90% of it is the main sequence because the rest is about 1 billion years. Everything else is 1 billion plus 10. So what percentage of a star's lifetime is spent on the main sequence? About 90%.
Nice.
Okay, in one HR diagram, we can kind of describe this whole sequence that I just talked about. So let's go through it on this diagram. So here's an HR diagram showing blue or high mass stars down to red or low mass stars. We're talking about a low mass star, which is everything from about here down to here. So like 1/2 of the range of stars in this diagram, including our sun. So let's consider what happens when the sun dies. So during that 10 billion years on the main sequence, helium is building up, right? hydrogen is fusing to helium, and that helium goes somewhere. Well, it's heavier than hydrogen, so it sinks to the center of the star. And we say it's inert because initially it can't be fused. It doesn't have enough temperature to fuse helium yet. So what you're building up eventually is this giant core of just helium, like a big block of helium in the center of the star. And that causes a problem with what we call the solar thermostat. That is, normally, before there was this giant inert core of helium, we talked about how if the core gets too hot, it can just expand and cool off. And that's important because if it gets too hot, fusion goes more rapidly, which makes it hotter still. And it's a runaway scenario where it gets hotter and hotter very quickly. But luckily, normally, the core will just then expand and cool off. But once you build up this core of helium, you can't do that. The core is now helium, it can't expand. So this is why a star exits the main sequence and begins this journey where it gets bigger and redder. And that's because its thermostat is broken. And the rest of its life is going to, as a result, go pretty quickly. So it's burning now in the shell of hydrogen, but it's burning more rapidly. It causes the star to kind of expand outward. And then at a certain point, it gets hot enough that the core of helium can actually start burning. So now it kind of briefly becomes kind of like a regular star again. So it comes back down this way, back towards the main sequence. But it's not on the main sequence, it's now burning helium instead of hydrogen, which makes it generally hotter. And this process, because it's hotter, goes more rapidly. And at a certain point, carbon builds up in an inert core. Okay, so now we have a core of carbon built up. And again, that causes it to lose its thermostat and it becomes a red giant again. So it enters this last leg here, goes up, becomes a red giant. It's all happening very rapidly now. All the remaining helium and hydrogen are fusing in what's called a double shell. So shell of hydrogen, a shell of helium, fusing. And the remaining few million years of the star's life finally runs out of fuel. What happens when it runs out of fuel? Well, it collapses. It collapses until degeneracy pressure takes over. And that's a pretty catastrophic event. A huge amount of energy is released when it begins to collapse. And it kind of blows outward its layers. It sheds its outer layers outward in what's called a planetary nebula. This is an example of a nebula that we see in these beautiful photographs that has gas and dust and can form stars in the future. What's left behind in the very center of that nebula? Often hard to see because it's so small, but a very blue, hot white dwarf. And that's that core of carbon, primarily, like a big diamond that's blue hot. And that will just cool off and get less luminous, less blue till the end of time. Okay. That's the story of a low mass star. And before I'll let you go a little early today. Let me just remind you about the process that goes on in the sun to allow it to be on the main sequence. That's called the proton-proton cycle. This is how it turns hydrogen into helium. So I want to remind you, first I have this little diagram up the right describing the fact that, remember, protons don't have each other. They're positively charged. Protons don't want to get close to each other. You need a high temperature so they can get close enough to each other to enter this region where they snap together. Okay? And so once you get the core of the star hot enough, you begin to be able to snap protons together. What's called the proton-proton cycle, where you snap two together to produce hydrogen-2. You snap another one on to produce helium-3, and then finally you snap two helium-3 together to produce a helium-4. That's regular helium. Plus two more hydrogen protons that can go back to the rest of the soup that continues the proton-proton cycle. And overall, the net energy out is 4 million electron volts. That's a unit of energy in physics. That is, you start off with 4 hydrogens, and you end up with 1 helium plus some of these alpha, gamma, and neutrino radiation that constitutes the energy that stars emitting. And that's what powers the star. This is the process that goes on during the main sequence of a star, low mass or high mass. Well, as we'll talk about in a high mass star, you often, in addition to what's called the proton cycle, you have the carbon, nitrogen, oxygen cycle. Is another way to produce this same reaction. So I'll end with this today, right? What happens when a star like the sun exhausts its hydrogen core supply? Well, it's no longer producing energy through proton-proton fusion. Right? So the core, because the core doesn't have the energy to create the pressure to cause it to keep the star stable, the core contracts. Okay, but as the core contracts, it emits a huge amount of energy because of all that gravitational potential energy has to go somewhere. Its outer layers expand, and it becomes a red giant. This is where overall the star gets bigger and brighter, and its surface temperature is a little lower on the surface. It looks redder, but overall the star is bigger and brighter. Okay, and that begins the sequence of the end stage of life of a low mass star that we'll go into some more depth next lecture. Are there any questions? So remember, you do have a quiz on D2L. Don't forget to check D2L. You have until Wednesday to complete the quiz on stars. All right, if there's no question, I'll let you go. I'll see you all on Wednesday.